All right, good afternoon, beautiful people. I have a confession to make. I'm not an Umbraco developer or user at all. The only thing I knew about Umbraco before coming here today is that the people are delightful. So I'm very honored to be here, and I hope this session is useful and interesting to you. So yeah, today we're going to be talking about authenticating your users over the web. This is who I am. I currently work for a research institute based out of Oxford in the UK. I help epidemiologists write research code. It's basically like DevRel, but for researchers rather than developers, which is really, really cool and interesting. But this talk comes out of when I used to work as DevRel for a company that had a web framework. We wanted to show off all the different ways we had of authenticating our users. And then I got actually genuinely interested in it, and then I wrote a talk about it. So that's what this is today. So to get started, we have to talk about what authentication actually is. We're then going to talk about common ways to authenticate your users and how you should choose between them. What makes an authentication system good? And in what context is that? How do you make that decision? So what actually is authentication? First thing to say is that authentication is not the same thing as authorization. Authentication you'll sometimes see referred to as auth-n for the authentication, and authorization, auth-z for authorization. Authentication is about deciding who somebody is. Authorization is about deciding what they're allowed to do. So, authentication. I have a web app, and I have some users, ideally, of this web app. I've built a web app, and there's some people who use it, because I'd like to, maybe make some money off of this thing. So I hope people use it. And ideally, I hope I don't just have one user, I hope I have lots of users. But my user, a given user, has some information that they want to store with my web app for ease of use, like payment details. Maybe they also have restricted actions that they're allowed to perform, such as posting under a given handle on a social media site. Now, I'd like to store these things. I'd like to have access and control over this data and allowing them to do these actions, because that's what my web app is for. And if I have lots and lots of users, I now have a problem, because I only want this user to have access to their specific data and actions. In other words, as a web service provider, I want to be able to verify that a given person using my service corresponds to a given identity in code or in my database that I've sort of determined, so that only the correct people have access to the correct actions and data. So how do we actually do this? Well, defining identity is really, really difficult, philosophically, not just programmatically, right? We have a hard enough time saying, oh, am I the same person one moment to the next, let alone when we introduce computers to the mix, because they complicate things, as they always do. So what we have to do instead of, grappling with all of these philosophical problems is we use abstractions, and that's what we do as software developers. These are only ever approximate, and they can fail. And the ways in which they fail determine which ones you're going to want to use. So we have lots and lots of different abstractions here. Here you can see you've got a username and password. That's probably familiar to a lot of us here. We've got things like biometrics. We've got identity providers, one-time passwords, and then OIDC login with Google and Facebook, and something that I've forgotten has been lost to time. Earlier we had X go and give it to you. I think the only thing X gives to you anymore is like ads for something nobody wants and online abuse. So anyway, but you can use existing identity providers such as social media sites or places like Google and Microsoft to log in, and we'll talk about how that works and why you might do it. This is a lot of options, right? It's pretty bewildering. How do we analyze all of these in order to know what's going to be best for us and for our users when it comes to authenticating them? I would like to start by taking a bit of a deep dive into something we're probably all familiar with, usernames and passwords. So the way this works is, I'm a user, I'd like to log into a web service, and there's a server that backs the web service. So you've got the client and server here. And I put my username and password into the client. That gets sent to the server. Without loss of generality, we're considering that all web traffic here is encrypted. So, just to head off anyone going, you can't send the password in plain text. Yeah, you shouldn't do that. Your username and password, your credentials get sent to the server. The server is able to verify that they're correct, send that affirmation of identity back to the client, and the client lets you in to see your data and allow you to perform your actions. So here, the abstraction is knowledge of a password is equivalent to identity. How can this abstraction fail? Who else knows that password? Well, ideally no other people, but in order for this flow to work, there are 3 elements that do actually need to handle, but maybe not store, the password. You need to know it. That's what this all relies upon. The client needs to at least pass through the username and password to the server, and the server also needs to handle the password and username. When we think about the server, it has some responsibilities. It doesn't actually need to store the password. What it does need to be able to do is to verify its correctness, and it needs to prevent anybody else from getting hold of that password. If your server can fulfill these responsibilities, it's able to act appropriately as part of that authentication flow. And a naive way of doing this might just be, let's just store the passwords. Here's Eli, and here's Eli's password. Obviously, this is bad because your server gets broken and all the passwords are leaked, and now attackers can log in as whoever they like. So we use hashes to obfuscate passwords, right? So we take a one-way function that takes my nice, legible, rememberable password and converts it into a string of sort of ASCII, let's say, or UTF-8 or whatever. And then we store that. However, if my password is something like Eli's password and you're using a well-known hash function, somebody could hash Eli's password, guessing that that might be my password, and compare it to what's there if your database is breached. So another level of obfuscation here is we use something called salts, where you append some random data to a password before it gets passed into the hash function, and you store that, usually not alongside the salted hash, but somewhere else in your system. And this is another level of indirection that makes it harder for people to crack passwords given a database breach. But what ends up happening is that if somebody does get hold of your salted hash, it's still game over, especially if you have used something like Eli's password. Any passwords that use recognizable words, common strings of characters, of which recognizable words are a subset, they're going to be easier for people to crack computationally because they're going to be some of the things that people are most likely to try. So what you end up with is the idea that all secure passwords look something like this, which is not very useful. I've given this presentation a bunch of times, I couldn't tell you this string, right? So we have to think about the user who has to know their password. What responsibilities does the user have? Well, they have to not tell anyone their password and they have to remember it. Users can forget their passwords, and therefore you have to have some kind of reset flow which could be abused, like that weakens your security, right? Users also can be tricked into giving away their password. This is what phishing attempts are. Someone will stand up a website that looks just like yours, and then the user will put their password into it, and boom, whoever owns that fake website now has access to your user's credentials. And they can be tempted to reuse a strong password. Let's say I did remember that big long string of characters. Next time I have to enter a password, it's going to be really tempting to just use the same one again, right? Or append a 2, 3 to it, whatever. And obviously this weakens your security because if someone cracks your password for one site and they know who I am, they might go and try that same password in all sorts of different services. And if I've reused it, they now have that for free as well. So all of these things are considerations when we think about if we want to use username and password for our users' authentication. Are our users particularly susceptible to these kind of things? How are we storing things in the database? And obviously there are a lot of plug-in services that we can use these days that have considered a lot of these for us. For example, like storing passwords in a database. It's not exactly a solved problem. People get it wrong all the time, but you don't have to roll your own. But when you come to think about your user experience of your website, if it's a pain to log into your website, maybe people aren't going to do it and they're going to visit your website less. They're going to go to some other online shop selling tea, and you're going to lose out on business. So how can we do better than that paradigm? Well, we've talked about abstractions and the fact that identity is, we abstract over it in order to be able to program things that deal with identity. And these abstractions are called authentication factors. So knowing a password is an authentication factor. What multi-factor authentication does is it says, okay, let's not just use one thing, let's use multiple things. And most commonly this is 2. You'll see the acronym 2FA for this. Basically, we use multiple abstractions. 1 can fail, 2 is less likely to fail, right? And in order to make this as strong a concept as possible, we have these different ideas of types of factors. So a username and password would be something you know. But you can also own things like a phone or a YubiKey. You can also be things like biometrics. And so we have these 3 categories of ways to abstract over identity. Now, when we use multi-factor authentication, it's much better. Like if we use 2 things you know, the method that somebody uses to compromise the first one, they may well be able to use to compromise the second one. You know, they've got you locked up in a basement and they're trying to get your crypto wallet password out of you. If you've just got 2 passwords, you know, it's not significantly more difficult for them to compromise 2 passwords than 1. So we like to mix and match between these categories for maximum benefit. So, for example, it will be much better to have a username and password and get a one-time password sent to your phone, a thing that you own. This is better than using things from the same category. So what are some options for multi-factor authentication? This is pretty much the bulk. This is the next section of this talk, is running through some options, some paradigms for authenticating people. My favorite one is hardware authentication tokens, because they're really, really cool. So what these are things that look like a little USB drive, YubiKeys. There's lots of other brands of sort of hardware authentication tokens that sort of plug in or use NFC or something. They can also be built into your devices. So most laptops now have one. If you use Windows Face ID, for example, that's using a hardware token, or it's using some of the same sort of technology there. Phones use them as well, and these are called platform authenticators. For the rest of this section, I'm going to use the little USB thing just to be extra clear about what I'm talking about. Now, the way that these work is they're based on public key cryptography. Do I have mathematicians in the room by any chance? Oh, no. Okay, cool. I love public key cryptography. I have a whole talk about the maths behind RSA and elliptic curve cryptography. So I think this is some of the coolest maths out there, basically. What public key cryptography allows you to do is you have a private key and you share a public key. And then, if you want to prove your identity to somebody, you can use your private key. And with a hardware token, this is embedded intrinsically into the hardware of this token. You can use it to sign something or to encrypt something. And then anybody with knowledge of your public key can use that knowledge to verify that the thing that you sent was indeed signed or encrypted with your private key, right? You can prove that you have knowledge of a secret, or in this case, a physical ownership of something that's like it's the same device, without having to give away that secret, which is really powerful because it means you don't suddenly have to, like, it's not the same as a password. It's something that I can use, that somebody else can know that I've used, but they don't have access to that same usage. And the thing about hardware tokens is they are the public-private key. The private key is embedded in it in such a way that it's functionally impossible to retrieve the private key from the device, at least without destroying the device, and even then, you've got to know exactly what you're doing. So it's a very high level of tying a physical device to a sort of technical code object, right? So the way that this works is, let's say I have built a web app that uses this as an authentication method. My user hits the button saying they'd like to log in, and my client sends a request to the server saying, this person would like to log in. And the server goes, great, well, I have a hardware token registered for them. I'm going to send something called an authentication challenge back to the client. And this authentication challenge contains data about like what the web app is that you're trying to log into. And then the web app says, hey, user, we think that you have a hardware token. Can you present it to us and use it? So the user does that. They plug their hardware token into the computer. And then that authentication challenge gets sent to the hardware token. And then on that hardware token, not on your computer, not on your browser, not on your laptop, on the hardware token itself, that cryptography is performed. And the authentication challenge is signed by your hardware token. That then gets sent back to the client, which sends it to the server, which has knowledge of your public key, and it can use it to verify that authentication challenge. That verification is then sent back to the client, and the client goes, brilliant, you have presented the correct hardware token. We assume that this is the equivalent thing of you being who you say you are, and I'm going to let you in to see your actions and your data. That is how hardware tokens work. It's the maths behind it is super cool. The implementation behind it is super cool. I read through the FIDO specs a while ago, and it's just like, it's brilliant. And they are very, very secure, right? This is a sort of very difficult paradigm to break. So what are some considerations of it? Well, the device knows about the web service. The challenge, the authentication challenge that comes from the web app contains data about that web app, which means if somebody stands up something that looks very, very similar to mine, the hardware token itself will know that it's not the same thing. Computers are much more difficult to fool with a visually similar website than humans are, so they're very resistant to phishing attacks. The private key never leaves the device. All of that cryptography is performed on the device itself. The connection and the communication between the hardware token and the device that you plug it into or use NFC to connect through, that traffic does not contain the private key at any point. And the device can require user presence. So your YubiKey will have a little button that it requires you to press. Some of them even require that you have the right thumbprint to do so. And this means that if you leave your YubiKey plugged into a computer, that's not great. But what it does mean that if you leave your YubiKey plugged into a computer, even if someone's got malware on your computer, it can't just spam it with requests to try and reverse engineer your private key. You would have to be pressing the button every time to be signing responses to permit that to happen. So it's an extra level of protection against some kind of brute force attack. These are brilliant. Why isn't everyone using them? Well, you touch the thing or you use your fingerprint on your phone. Well, they're expensive. They are expensive to use. I think it's as technologists, we're probably the highest proportion of people who have these because they're cool and we know that they work really well and we have the salary to buy them for ourselves or our companies are willing to buy them for us. This is not true for most people in the world, right? The other thing is you can lose them. I did an episode of .NET Rocks ages ago with Rich Campbell and Carl Franklin where we talked about this, and Rich was telling me that he has like 5 YubiKeys or something and has multiple registered to each account so that he knows if he loses one, he can get back in, deregister the one that he lost, and he's got this whole system of knowing which ones are connected to which accounts. I have 1 YubiKey, and I have ADHD. So yeah, right, as do quite a high proportion of us in this industry. So this is a major issue when it comes to hardware tokens, is if you lose them, you've completely lost that authentication factor because it's tied to the physical device. Right, and there are things that are being done to mitigate this, for example, passkeys, which we'll come on to later. So yeah, that's hardware tokens, right? And you can have them on your phone and they can be tied to a fingerprint as well, which is extra nice. Another option is one-time passwords. This is another thing that you have because it relies on your phone. So the way that this works, sometimes you get them through the email as well, right? You get a text to your phone. The way that this works is I go to my web app and I say I'd like to log in. The web app says, okay, I'm going to ask you for a code. It says to the server, please send a code to this person. Server says, right, we have a communication channel on file for this person, a phone number, an email account. I'm going to send the one-time password to that channel. The person reads it, enters it into the app. The app goes, yep, that's correct. There might be an extra server call in there, but and lets you in. Very, very simple. One-time passwords mean that you don't have the possibility of, this is only valid for a period of time, potentially only a single number of uses, like a low number of usages. So uses. So it's the risk of password leakage is mitigated enormously with this, but they're kind of annoying to use, right? And if you have no internet or no cell service, no phone service, you'll be running down the street holding your phone up to the air being like, I just want to log into my bank, please. That has happened to me before. The other thing that is an issue with these is that SIM data can be cloned very easily, trivially, particularly in the States. I think there's no overarching service that determines that only one person has access to one phone number at a time. If I know that, maybe someone I'm targeting is registered with O2, I can walk into Verizon and say, hey, can I have this phone number, please? And they can just do that, and they can just give you a SIM card. It might be a little bit more complicated than that, but not much. It's actually very easy to clone SIM data. Reddit had a breach due to this once. And of course, you can lose your phone. I once had my phone get run over. The SIM card was fine, but the phone wasn't. So, drawbacks, things you need to consider. At all of these authentication mechanisms, you need to have backups built in for somebody to recover their identity in the event that they lose access to that authentication factor. Magic Link login works very, very similarly. This is usually via email rather than phone, but it's a very, very similar thing. Slack does this. Has anyone here not used Magic Link login ever? Cool, yeah, we all know what this is. You go to the thing, they say, okay, give us your email, we'll send you a link. And if they have you on file as a user, they send a link to your email. This contains a link to authenticated session with some kind of token, usually in the query parameters. And you click that and you log in. And this is slightly nicer than a one-time password because you don't even have to type in a number, right? It's just you click it and you're in. And if you're accessing the web, they assume that you have access to your email. So it works pretty well. I really like this. I think it's underused. However, you can lose access to your email address. When I worked at Anvil, the company I was at when I wrote this talk, we had a lot of people who signed up using student email addresses. And I know that when I left university, I did not make any attempt to keep hold of that student email address. And this was a perennial problem that we had with people saying, well, this was my primary identifier for my account with you, and now I don't have access to it anymore. So that is a consideration. Email addresses are not actually permanent, even if I have had the same one since I was 13 or something. Right. So those are all multi-factor authentication options. And if you want to be secure on the internet, you will be using at least 2 authentication factors wherever you can. Now, if you think about how many online accounts you have, I do still have an X account. I'm on Blue Sky, I'm on Facebook, I'm on Tumblr, I'm on whatever. I'm, signed up to 1 million online shops to go and buy little tchotchkes and yarn and whatever. And if I used 2-factor authentication for all of them, it would suck up a significant amount of my time to go and set that all up. It's a pain. Also, if you think about how many accounts you use during your work life, you've got, Slack, whatever HR system you use, you've probably got some like G Suite or Microsoft or something that you're using, all of these different things, tools that you use in order to do your job. And, if you're an administrator for that software company and somebody loses access to any one of those accounts and it's your problem, that's going to be your whole job. So how can we make multi-factor authentication more user-friendly? Well, one of the ways that we can do this is by having single sign-on. And this is the paradigm where you have essentially one place where you authenticate, and then everything else trusts that authentication. So the way this works is you have your service provider. Let's say that this is an online app where I'm going to go and buy some tea, because we all love tea, or maybe coffee, some kind of hot beverage. And in order to log into this, I've built this web app that lets people buy tea. Well, I don't want to handle user authentication, so what I do instead is I delegate this to an identity provider, somebody like Google or Auth0 or Microsoft, or maybe I've got there's many options that you can use. And the way that this works is your identity provider is a single nexus for this stuff, where you can have one place to implement all of your multi-factor authentication, and also one place to handle anything that changes with respect to that user's identity. For example, people get married and change their names. People acquire new genders and change their names. People move houses and have different addresses. People have new payment details and so on. You can have one centralized place where all of this gets updated, and then you can see the benefits of that across every service that delegates their authentication to this service, right? This is brilliant. It saves a lot of trouble. However, so the way that it works is somebody comes and wants to buy tea from my website. And I'm that website, and I say, cool, you want to log in? I don't do that. Go to Google, and they'll authenticate you. And they go to whatever Google account. You've seen that little modal that pops out, like which Google account would you like to use? And they go, that's what happens here. They're redirected. They authenticate with Google. And then, that's where you do your multi-factor authentication and all of that. And then you authenticated there. Then that identity provider redirects you back to whatever service you were trying to use with some kind of token that service is able to use to verify that they can trust this authentication that's just happened, this event that's just happened. And then they let you in. Brilliant. It's delegating authentication. That is what single sign-on is. It means that you, as a web service provider, don't need to store users' credentials. You don't have to worry about salting and hashing passwords. You don't have to worry about any of the reset flows for all of these things. That's all the problem of the identity provider. Users don't need to remember lots of passwords. They have one master password, let's say, and one hardware token. But, of course, I'm sure you're all thinking, here's the big problem with this. What if your identity provider gets popped? It happens. These are organizations with big budgets and security, like some of the best security experts out there, but it can happen. And if that happens, everything that uses that is also compromised. So that is the risk that you're running when you put all of your eggs in one basket, even if it is a very well-funded, well-organized, well-protected basket. How do we implement this? There are 2 main methods that people use to make this happen. They are called SAML and OIDC, OpenID Connect. SAML stands for Security Assertion Markup Language, I believe. Has anyone ever implemented a SAML system before in this room? That's quite a high proportion. I am so sorry. Let's talk about SAML. So SAML, the way that it works, and there are some cool aspects of it, but you'll see why I said I'm so sorry. So if I'm somebody who's trying to log in to a service that uses SAML as its single sign-on mechanism, what happens is I go there, and I say I'd like to log in. And then in my browser, I am redirected to whatever identity provider they're using. And alongside this redirection, I am given some XML to carry with me, some SAML, right? An authentication request. And before this is able to happen, the service provider and the identity provider have needed to set up a relationship between them. Part of that is exchanging SSL certificates, essentially, so that they can use public key cryptography to verify their identity with each other. So this authentication request is cryptographically signed. This will be relevant later. The SAML identity provider is able to verify that this authentication request comes from a service that it knows about, and it is able to say, okay, you signed in, you've logged in, you've done your YubiKey, your password, whatever. And then it redirects you back to the service provider, and the token of verification that the service provider is able to use is a SAML authentication assertion, also cryptographically signed. The service provider is able to use their knowledge of the identity provider's public key to verify this and say, okay, you've authenticated with the identity provider that I know and trust, and you can be logged in. So these two entities, the service provider and the identity provider, never actually interact directly. They don't have to have any ability to communicate with each other. It's all happening through the user's browser, which means that your identity provider can be on a secure network as long as the user has access to that secure network. It can be inside your company VPN, for example. This is useful in some cases, and this is something that is not provided by OpenID Connect, for example. However, this is all dependent on the idea that you can sign XML data cryptographically. And it's really, really hard, because signing something cryptographically, it works over signing bytes. And SAML, these two things are exactly the same semantically. These two things mean the same thing, right? But they're different strings of bytes, and they would have a different cryptographic signature. So they both mean the SAML issuer is whatever's in between these two, angle brackets things. But they would generate different cryptographic signatures. This is a problem. The way that we overcome this problem is with something called canonicalization algorithms that take these two different things and output some kind of logical structure that you can do a cryptographic signature over, right? And so this is great. We've understood that these two different things really mean the same thing, and we can do our cryptography over that instead. However, this is canonicalization. If you read the SAML spec, which I don't know if I'd recommend, but I've done it, you'll realize that there is no single best practice for canonicalization. There is no single algorithm for doing this that is recommended in all cases. So you'd better hope that your service provider and your identity provider are using the same ones. This is overall the issue with SAML, is that there's no real sort of hardened golden path for using it. It's extremely configurable, and you can do some really weird and wonderful things with it, which makes it very flexible. It also means it has a very large attack surface. But for a long time, this was the way that people did single sign-on. Then we came up with OpenID Connect, and the world became a much better place. So the way that OpenID Connect works is it's very similar. Again, you sign in somewhere, and a token is given back, and you can use that to verify identity. But it's a little bit more complex and in ways that give you better security properties. So this is always OpenID Connect. If you see this, you can log in with Google, Facebook, and something else. I should update that. So OpenID Connect, instead of using XML as its sort of language, it uses JSON Web Tokens. These do have standard formats, and they are much easier to generate cryptographic signatures over. So that canonicalization problem basically goes away. Also, the issue of, so in this scenario, tokens are parsed by the service provider. So the token of authentication, my tea shop can go, cool, I've received this token, and I think it's okay. But if they want to double check, they can check with the identity provider directly. They can communicate directly. This means that your OpenID Connect identity provider can't be on a secure network that your service can't reach, but it does give you an extra layer of security, and you're able, as a service provider, to verify the information you've been given directly with the source. So the way it works is somebody comes to my tea shop, and they want to log in so they can buy some tea, and I pass them over to Google, let's say, but any OIDC server. And they're redirected in their browser to an authorization endpoint. Now, if they're already logged in with like their cookies, this is sort of a very quick thing. If they're not, this is where they do their YubiKey, their password, and so on. So they're authorized there. They then get sent back to the service provider with an authorization code. Remember, authorization and authentication, not the same thing. What the service provider then does is it takes that authorization code and goes straight to the OIDC server directly. The user's part in this is now done. And it goes, hey, I've been given this authorization code. Can you verify that you issued this and that it was somebody that you know about? And the OIDC server takes that at its token endpoint and says, great, that's true, that's correct. That was an authentication event that happened, and I can generate you a token that that user can then use to log in. So then they send something that's called an ID token back to the service provider. And the service provider then says, brilliant, I've double-checked that this is who they say they are, and I'm going to let them in. You can also do something past that point where if you want to know more information about the user, or if you want to know more information about the authentication event that happened, where they actually signed in, you can send that to something called an introspection endpoint. So there's many more ways for your service provider and your authentication server to interact that can be very useful. It makes this a very extensible process. And so the identity provider can verify that, and then the person is able to log in and buy their tea. So, already talked about this, they communicate directly. This gives an extra layer of protection against somebody, against any kind of man-in-the-middle attacks, somebody pretending to be one or other of these parties in this flow. And it's also extensible. So there's things like user info endpoints where you can say, okay, this person's logged in, and if I go to the user info endpoint, they've actually configured their account with Google, Microsoft to say, yeah, this service can use my address info, my whatever. And we're dipping into authorization rather than authentication here. And that's because OpenID Connect is built on top of OAuth, which is actually an authorization framework. And so we've sort of added this layer on top of it just for authentication, but you can actually use the other properties of OAuth in order to extend this, which is really cool. And this is the main mechanism that people use for single sign-on these days. Right. We talked about public key cryptography a couple of times so far, hardware tokens, and it's also used in all of these SSO authentication flows for identity verification. With hardware tokens, much as I love them, they are tied to a physical device which is very losable. Passkeys are an attempt to mitigate that. And what a passkey is, and this is the passkey symbol, I put it in my slide's theme colors because I'm fancy. What passkeys are is they are a public-private key pair that is not tied to a specific device, that's encrypted with something else that you use to do encryption, and stored somewhere. Very vague, right? And one of the things is because they're not tied to a specific device, you lose that security property of it is, in theory, much more possible to get hold of this private key. It's not, you'd have to destroy the YubiKey to get it. But there are extra mechanisms that we put in place to make that very difficult. And the first of those is that we've encrypted it with something. I think when you use passkeys with Google, they encrypt it with your Google account's password. So people call this passwordless authentication, but the password is still there. We're still haunted by the sins of our past. You can decrypt and use these key pairs, and you can have multiple of them as needed. So if I wanted to use a passkey that I'm stored in my Google account, you log in with my Android phone, and it would say, you want to use this passkey to log in? Cool. Will you just give me your thumbprint? And then it uses that method of verification to say, cool, I'm now allowed to decrypt and use this key pair to log in. At the moment, storage of these key pairs is, you can do it yourself. You can stand up like a Bitwarden or something and do it yourself. But you have to really know what you're doing, and that's not an option that's really accessible to most normies, right? And at the moment, the way that most normies are using them is through some kind of cloud identity provider account that they have, Google, Microsoft, Apple. So the way that they work, somebody wants to log into a web app, and the web app goes, cool, you have a passkey registered. So whichever passkey provider you're using, whether that's your own Bitwarden or it's Google, it sends a message to there and says, hey, this person's trying to use their key pair. Can you go to them and find out if this is okay? And so Google sends a message to my Android phone and says, you're trying to log into this service. Can you let me know that that's okay? An authentication challenge pops up on my phone. I use my fingerprint or whatever other authentication factor I have registered there, and my phone says, yes, cool. That yes, cool is passed back to Google, Microsoft, Apple, Bitwarden, whatever, And then that is then funneled through to the web app, which lets you in. And so it's this sort of daisy chaining of security, where the security of your phone and whatever authentication method you have on your phone or your Windows Face ID is being used to unlock an authentication factor that's stored elsewhere. This is pretty good for a lot of reasons. It protects against device loss. If I lose this phone, I just need to get another phone that I can connect to my Google account, and all those key pairs are the same. I don't have to go and reset them on all of my tea shops and yarn shops that use them. It also allows you to do something called user verification, which is a stronger thing than user presence. So a YubiKey where you have to press a button, anybody can be pressing that button. With my phone, it wants my fingerprint. So that's a stronger security property. At the moment, you're currently largely dependent on big companies for this, unless you want to go through the faff of running your own passkey server, which is, you can do it. Technically, you can do it. And for some people, that might be the right choice. But at the moment, there aren't really any sort of, and this is something that is being built. There are more sort of vendor agnostic passkey storage solutions that are not running your own, that are cropping up, particularly since I wrote this talk. When I wrote this talk, it really was, Google, Microsoft, Apple. You've got to decide where to store them. And you've got to decide who you trust to store your passkeys. And maybe that's only you. But I have a much lower security budget than Google does. So, finally, with about 8 minutes left, we come on to what makes an authentication system good. And I'm going to give you a spoiler alert for this one. It's a lot of it depends. Who'd have thought it depends in a software talk? So things that you want to consider, obviously security. If your authentication system isn't secure, why bother having it? Now, when implemented correctly, username and password is pretty secure, right? Nobody else knows the password but your user, unless your user, gives their password away or reuses it and has it stolen. But what you end up with is a user needing to remember things that look like this. And not just one of them, lots of them. And this is really hard. And of course, password managers make this a lot easier. I fully recommend everybody use a password manager. They're built into your browsers now. You can have ones that are more, sort of configurable, controllable, store them elsewhere. But it's this is an intrinsic issue with passwords, right? Is that somebody has to remember a long, secure string. This is not very user-friendly. But if implemented correctly, it is secure. So we don't just care about using things that are secure. We care about people being able to use the things that are secure. Usability matters. We don't want people writing, storing their passwords in a Google Doc or something. Post-it note on your computer is not as bad as most people think, but if you work in a shared office, it's still not great. So if something is hard to use securely, that's a poor security property of it, right? It makes it less secure. Now, you might think my users are techies. They're fine. They know how to use things, right? I used to know somebody, used to work for somebody, genius, right? Co-founder of a successful startup, PhD in database design. He pasted his master password into Slack. So you may think that, and he had to go and reset it, and you may think that your users are techies, but you have to have allowance for things to go wrong, because they will. So things need to be easy to use. If implemented correctly, SAML is really user-friendly, right? You as a user go to an identity provider, you log in, and everything's peachy. The real issue with SAML is that it's a pain to implement correctly, and it's got a very wide attack surface, and you as a developer who's responsible for a SAML system have got to keep a lot of things in mind in order to make sure that you don't have security holes, and there are all kinds of horror stories you can go and read about SAML going wrong. So it's not just about users' quality of life, it's also about ours as developers. If something is hard to implement securely, you're probably not going to implement it securely, so it's going to be insecure. So we need to consider things like, is it easy to implement? Is it easy to maintain? Is it easy to stay up to date with latest security fixes and changes in the landscape, right? The advent of security tokens, hardware security tokens, changed a lot of security postures. How easy will it be for your system to adapt to those to enable people to, use better things that give them better security? So when we think about these things, these are the things that go into the it depends. These are the things you have to consider, and they're going to vary based on your specific circumstances. So when we think about it depending, here's the things that it depends on. Who are your users? Do they have hardware tokens? Are they likely to have stable email addresses? Are they going to have consistent phone coverage, right? If I live You know, when I was in undergrad, I went to Cambridge and I lived in a college where there was absolutely no Wi-Fi. So getting one-time passwords through my phone to log into my bank, I had to go outside to do it. And that's a very privileged version of this. Like maybe your users are people where there isn't consistent phone network anywhere, and not just because they're in a really old stone building. What's your security posture? My little online tea shop is probably not going to be subject to some really sophisticated security attacks, unless for some reason people think that my users are reusing passwords that are being used in more important places. But someone like Google, they have a really big security budget. They have some of the best security experts around because their security posture needs to be absolutely watertight. You need to think about what yours is. Are your users people who are particularly likely to lose their hardware tokens? Things like this. And we go back to what are your users? Obviously, these things are all interrelated. And finally, when we think about ease of implementation, who are your development team? What skill sets do they have? What's your dev budget? Can you get in a contractor to do security audits? All of these things factor into the choices that you'll make about the software that you build and how that software operates in the real world. Because none of this is any good unless it actually provides benefits to you and to your users, and ideally gives us a paycheck to take home at the end of the day so we can spend it on tea and yarn. So that's the it depends, right? So wrapping up, we have learned, hopefully, some things. What authentication is, and why we need it, so that other people can't get hold of our credit card details and post as us on social media websites and, you know, spend our money on things that we wouldn't have spent our money on. How we do it and all the various options that there are, the various ways that they work and their security postures. And we also learned why it's hard. Who knew about the XML canonicalization thing before this? That is fewer people than have ever implemented a SAML system. Just saying. And we've talked about how we do it well and the considerations that you need to take into account when you're choosing the methods that you use to authenticate your users for your web service. Usability matters, not just for users, but also for us. And like everything in software, really this is a people problem. And you need to understand the people in your systems in order to make the correct choices, or at least the best choices. So, thank you very much for your time and attention. That QR code takes you to a little feedback form, not just for questions, just anything that you want to say, completely anonymous. So please feel free to use that and get in touch with me. Do we have any questions that have come through on the canonical way of asking questions?
Yeah, no.
No questions?
No online questions.
Well, if anyone has them, now is the time. You've got 2 minutes. Otherwise, go and get a head start on coffee.
Thank you so much, Eli. Like you said, if anybody has any questions or want to chat more to Eli, you'll stick around for the next few minutes?
Yes, no, I'll be here. I will try and be around sometime over the next 2 days, but I am in theory working my day job, so...
Sounds good.
Depends how much I slack off from that.
Thank you so much. Now there'll be a break here, and we start again at 3 o'clock with the next session. Let's give another round of applause for Eli.